Okay, well, hello everyone. This is the UC Center Sacramento Speaker Series. I'm Richard Kravitz, Director of the Center, and pleased once again to welcome you. This is actually the conclusion of the summer portion of our series, and with that we wrap up our focus on the three themes for 2019-2020, which I'll elaborate on in a minute. One reminder, after today's speaker, we'll have time for question and answers. Please reserve your questions until the end and raise your hand and you'll be called on to deliver your question live after identifying yourself and your affiliation. So that'd be really helpful. So with this lecture, we're finishing up one of our 2019-2020 areas of focus, which is using big data to inform public policy in California. We've seen how social media and information technology can produce bad outcomes in politics, security, and commerce. And 4 major tech company executives are now answering for some of these problems in Congress as we speak. But big data can also be channeled in the service of positive social ends, and in particular to help guide public policy. And that's broadly what today's talk is about. So to do that, I'm pleased to welcome Professor Marta Gonzalez. She's Associate Professor of City and Regional Planning at UC Berkeley, and also a physics research faculty member at Lawrence Berkeley National Laboratory. She has a BA, MS, and PhD in physics, and her scientific specialty is the statistical physics of complex systems and network science. Her work focuses on understanding and addressing urban problems in the world's most challenged cities. Her recent research uses billions of mobile phone records to understand the appearance of traffic jams and the integration of electric vehicles into the grid, smart meter data records to compare solar energy adoption policies, and card transactions to identify habits in spending behavior. She's received numerous honors, awards, and grants from organizations such as the UN Foundation, the Gates Foundation, and the MIT Phillips Lightning Grant Challenge. She's published many articles, including one on the topic of this lecture, which you can see in the slide in front of you, recently published in the highly ranked journal Nature Communications. So please join me virtually in welcoming Professor Marta Gonzalez.
Thank you, Richard. Hello, everyone. I'm very happy to be here. Thank you for being here in the summer webinar. And as Richard said, the aim of this work and in general of my work is how to use this information, digital information that we live. Our privacy is gone because we are constantly gathering information. We live that information. And it became a passion and a career. How do we use that for other applications that not necessarily are towards the funds of the companies? Like the mobile phone company give us a service, they have the revenue. But if we use that data, it can be used for other purposes. In particular, today, I'm going to talk about the first application I did in how to use mobile phone to improve the estimates of how many people we have in buildings. And the art of this type of questions is that it doesn't come ready. So it's not as easy as count the phone numbers, give me the data, and that's it. That's how this research required. You see the many authors. It requires several steps and angles in this viewpoint. On the top part, we see the students that made this research possible. And in the bottom, you see the advisors. Then Ed is professor in UK. He put everything together. Carlos is in a architecture firm right now. He graduated with his PhD. He was in charge of doing all the energy modeling, Sid, cleaning the phone data, Ed, the driver of the bus that put this all together, and Christopher Reinhardt is the architect that does the building energy models without phone data. I myself am the expert of creating these mobility models with phone data, and just Lynn funded us to do this attempt. Nobody had married the phone data world with the building energy models world. Then here is the aim. Here is the city we were working at, because this work was done in the transition when I moved my group from MIT to Berkeley. And then that's how you see everything done in the Boston area. The Boston area has 3.5, not the small city of Boston, but the Boston metro has about 3.5 million people. That's the area we want to focus on. We have phone data from them, from all of them, of one carrier. Then is 1 million phone users in all this area. And the question is, when people is not moving, they are in buildings. When they are in buildings, they are either residential buildings or commercial buildings, they are using energy. Depending on where they are, different patterns are out on the energy models. So how can we estimate that occupancy? That's the question. Better, more specific, can we use the mobile phone data models for that purpose? Then I'm going to tell you briefly about what is it that was not using phone data. What are these weird energy models of buildings about? What is the phone data we use? That at the end is really a model, because we need to take account everybody, not just the raw data. And then the last point is exactly how we have our estimate, how we evaluate them, and how we really trust if they were good or not. That's the important aspect, and that's the reason it was not obvious to see if our results would be how to validate that. That's how, working with the Boston energy model that was already existing, we could do this application. So from an idea all the way to the data to an application, feel free to start thinking. I will be looking forward to discussing with you other applications, innovative applications for social good we can do with the phone data. Then first, why we are interested in estimating, given a city with all the buildings they have, what we want to estimate the energy they consume. It turns out, in the process of consuming this energy, they take into account, they produce a lot of CO2 emissions due to the import of the energy. Mostly into we are not doing the construction part, mostly into cooling and heating. Heating in the winter, cooling in the summer. In the Boston area, we have very hot summers like right now, and very cold winter. So it's pretty intensive, this consumption. And not much has been done in the estimates of, you do something to a building, how it's going to reduce. And it's a complex process. So we believe that bringing big data technologies into these estimates is going to have impact. Otherwise, we're going to be stuck into an old way of thinking and gathering information. To our goal, our dream from engineering and planning is, at the end, we produce something that is converted into a policy. That's why I was particularly excited to be invited, and that this paper captured the attention of the center. Then, you have a map, you have all the buildings. Based on the area and the temperature outside, they are modeled, existing models. In fact, the standard model in the United States used by many researchers around is the Energy Plus model. It was funded by the Department of Energy, and it was born and maintained very much into the LBNL, just very close. And if we have the building, we have the weather, we have the materials of the building. Is, in a nutshell, a physics-based model. Then what do we need to have as an input apart from the buildings and the weather? We have the whole physical part. If you think about it, it's good because it's a transportation problem. However, the part is not very clear into the Energy Plus model is, given a building, given the temperature, the occupant, what's going to be doing? How many occupants this building have, and what is the set point temperature, and this type of thing is somehow the unknown factors. What are the type of outputs that Energy Plus give us in general is the energy consumption of buildings. Look in the pie chart at the end, heating is already 47%. And then cooling is about 6%. Then that is cooling and heating is the majority, and the rest is the electric consumption as for lighting, appliances, cooking, and hot water. So basically, at the end of the day, if you want to model the energy consumption in buildings, you want to have how much gas and how much electricity. Exactly what appears in your bills, distributed. The physical part of Energy Plus, they take into account everything, but particularly the heating part and the cooling part depends a lot on the physics of the building and how many people is in there. Then, for the how many people is in there, this is what you're seeing there is 30,000 points. These 30,000 points that are moving is a model, but it's a model in which when you are staying in a location, that information is used from mobile phone users. So basically, in the mobile phone users, all of us generate points, signals. I'm gonna show you how it looks like. That right now that I'm sitting here talking to you, my phone is generating signals, and then they know I'm staying here in a region. If I move, they capture that. It's not perfect, it's like a cloud of points. We convert that into what we call a model. So basically we clean the data to see a region where the person is staying, when it's moving, and when it's staying again. Well, the result of this clean version of the data is what we call a model, but the important, what it makes very exciting for me is that these points is a model, but is generated by actual users. If I have a recommendation, the mobile phone company can send the recommendation to these users. I cannot, but the company could. So somehow, it's not very hypothetical models, it's data from all of us that we are giving out our digital information for these purposes. So here I'm showing more details on the model. In the left-hand side, this cloud is how the data looks like. We have P1, P2, P3, P4, etc. It have longitude and latitude and time. So the users move or stay back. To give you an example, if you see, this is, imagine is mere P3, P4, P5 is somehow a longitude and latitude around a place where I am, which is right now a stay one. Then for periods that every single user stay in a place is what we call a stay point. And then there is a technique called parsing trajectories that give me every day, every hour, a stay point if I'm not moving. Tomorrow, I'm gonna see that for signal reasons, when I stay, I have a stay 2 and I stay 3. So what we do is using the regularity of users to find the stays, points, and create regions. Guess what those regions are home, work, or other. If you repeat that, we call those our frequent locations. And if you are the first time staying in a place, it's an exploration. So every mobile phone user has now the frequent visited locations and their explorations. If you have, in this particular case, we have 1 million users, 200,000 of the users are so active that it's almost like a GPS. So we can model them and validate our model because it's like almost all the time we know where they are. Then basically, we translate this cloud of points into a stay location. Then you have your home, your work is defined where if you commute there every day, and we call other, everything else that you go back. And that is basically what we have. Then what is the other aspect? That we got 3.5 million people, but the provider didn't give us every single person in Boston. And for energy purposes and also for traffic, we need everybody. Then here it comes what we call expansion factor. What we have in the right-hand side are the census tracts. And then to answer the question, how many people per phone user? That is the expansion factor. Light purple is between 0 and 50. And then we have the distribution down here. It's about 23. So the typical number is for every 23 person in a census tract, people in a census tract, you have one mobile phone user in which you know their day. Without asking, without knowing, you know the typical behavior, commuting and all. So basically, in this PNIS 2016, you have the entire framework, how to go from this cloud of points to what it looks like. The video I show you, that it looks like a video game or an agent-based model, just based on cleaning the data and extracting statistical features. How to do it is exactly in this paper. Is not the goal of this talk, but the goal of this talk is, okay, now we have this movie of where all people is at the census tract level. Let's try to use it to infer statistically. If they're staying, they have to be a small portion in a park, but most of them are in a building. If we have the data of buildings, how we distribute them. Then we have the time geo model, the mobility model in all the Great Boston area. Then you zoom in Boston. This is the city of Boston. And here is a neighborhood we focus more, that is Back Bay. Let's think first in the type of buildings. The majority of the buildings are residential, but we have all types and of residential single units, and then multifamily, etc., and mixed use. So we have an area in which we can have in maps. Now, every day, many researchers have these buildings with the mixed use. How are we going to distribute? This is the core challenge I introduced today. If I have the amount of users staying in a place, how we distribute them into buildings. And this is my story on how we address this problem. Here is the first part. In Back Bay, here is a density plot of all the people staying there. Notice, for example, here in Commonwealth Avenue, these little clouds, more people there. This is not that people is in here all staying together. The detail is, and this is the main challenge, the phone data doesn't give you the exact location, GPS style. Or it gives you a region, as I mentioned, and the region is biased somehow by your measure, by your tool to measure the data, which in this case is the mobile phone towers. Still, mobile phone data comes at the resolution of mobile phone towers. Then basically you can see where the mobile phone towers are. Then what we're going to be doing is using what we know from the people and the type of buildings to distribute all the people in these buildings. We do it for 82,000 buildings, but I'm going to give you details in one particular example in one block. The first thing we need to do is not only we have the architect have the geometry of the building, let's say that is commercial, but in a commercial building, like in a mall, we have a lot of businesses. How we distribute that? Here we use another set that is very much used for people doing data science. That is the point of interest of Google. Now you have where all the cafes are, where all the banks are, etc. So those ones, they come in a very good address that you go to the front. Then for every building, we know all the point of interest. And a point of interest sometimes have different labels. So basically, based on the point of interest in the right, we simplify the labels. For example, a university can be a school or a university label. We call it a school. Then we simplify the labels and we use what is the standard of person capita per area. So how many people can a cafe per area has. So it's somehow standards. Then now we have the buildings, you put labels on it. We have the point of interest they have. The building have an area, and then is the standard of how many people is allowed given an area, depending on the use. Then we use the standards, which is a old way, together with the POI, that is a new source for this purpose. So far, so good. Now we have, if you imagine our cloud, mobile phone data is clouds, you can see the places where you're gonna put them now have area and how many is allowed. Of course, they cannot go to a cafe at any time. Then in few words, in short, we use the opening hours also from the point of interest of Google. As you see what they use to advertise businesses, we are using it to label the allowance of our buildings for energy modeling purposes. So that is the way we do it. And here comes the challenge. Remember those regions where we think everybody is just right here? So this cloud, our task, core challenge is how we distribute all people that seems to be here according to the phone tower in all these buildings. This is not a way that we are gonna know that everybody is distributed in the right place. This is an estimate. What we know for sure is how many people is staging in this region with all these buildings. We're gonna do an exercise of distributing the people along the buildings to have an idea of the energy models. Then basically what we know from the people staying there, if they are doing a stay that is residential, a stay that is a work or other, as I mentioned before. Then if you're in the home, definitely you're gonna be put, the user is in the home stay, is gonna be assigned to one residential building. If you're in work, you can be commercial and industrial. And if you're in the other activity as a phone user, you're gonna be put in a commercial. So we know the label of the activities, and then depending on the activity, we choose like a lottery, the buildings. And here is, I would say, the main intellectual contribution or trick that worked. And I mean, this is how we did it, and it worked nicely. First of all, we grouped the buildings in clusters within a walking distance. And then we overall, basically this is divide and conquer. We have everybody together and we need to place them in clusters of buildings. In this example, you have a cluster with 52, 23, etc. buildings. Then the question is, if you have a cloud of users, how you're gonna distribute it between the buildings? And is the fraction of the total capacity. For example, here we have a big mall. Then the question would be, do you think that a commercial area, if people is doing commercial other type of activity, and we have this big mall, what is going to be more attractive, this part or this set of blue buildings? Then basically we add the cap I is the capacity of this cluster. Then most of our users are going to go attracted based on the size of the type of building. But the key is that's not always true. Sometimes you have small places that attract a lot of people. Then basically this was the idea to do that. We have this fraction, but we have a non-linear scaling. Then by the referees, they say, why 1/2? The truth is because it worked. It has to be less than 1 and 1/2 work. Then the referee said, no, do a sensitivity analysis, and that's why we have a whole mu. Our original mu was 0.5, but it doesn't matter as long as you have this formula. So the trick is you cluster the buildings and then you distribute them based on the capacity. Very simple. The way we work, we treat this as numbers, all the data available, and we just do a statistical test. We cannot ask the users. Then after you assign the user to a cluster, then you put them in the buildings. And then, for example, per each stay, you add the phone users, let's say in the mall. And then you, after you distribute the people in buildings, you just add the occupancy. And the beautiful thing of the phone data is that you know from which time to which time this person stay doing other type of activity near the mall, and then we assign this person in the mall and we add everybody together. That's the test. It's a whole data assignment process. And here you see in the movie an example of after we do it, we only focus in the occupancy curves. That's what we do on this. Then basically you see in this census tract, we have the number of people in commercial buildings total. They go from during the day only, and the number of people in residential areas. So it's somehow, as is done by Google Maps sending you to the streets. We do this. We have the phone users and we assign them through the buildings. We don't do recommendations, we just do an estimate. And this is a movie how it looks like. And now we're ready to check our estimate. This is a new way. We only use POI, buildings, and phone data, and that's it. The big question from now on, I mean, we already did what we wanted to do. As a researcher, there is a second challenge. How I convince the people, the referees first, and then everybody that listens to my talk, that this method is good or even better than what it exists. Then, this is nothing but just to tell you an estimate at the census tract level, what we have. We can say at 9 p.m. in all these tracts, how many people are in commercial buildings? We're going from building to tracts again, adding everybody. Then we have from 0 to 300, and then this is basically the intuitive part. If you see this map with attention, is that commercial buildings are not occupied at night, they are occupied at noon, and the residential buildings are occupied most of the time. And this is what tells me the magnitude of that temporal aspect. So far, so good. Then we check the second thing of consistency check. What's the ratio between the maximum occupancy allowed in a given place, in a single family home, on a cafe, in all these single buildings? What is the occupancy that maximum that is allowed, the maximum occupancy at at noon that we observed divided by the maximum capacity. Remember that we're distributing people. It can be that we are overflowing the maximum capacity sometimes, or they're pretty empty. So by this plot, what we see that in the residential buildings, the estimates of the nominal capacity sometimes is up to, in a few cases, it's 5 times less, meaning sometimes people live in a place and according to the model is, it's a 2-bedroom, probably it's gonna be living 3 people, and it lives many more people. So that's basically the happen in college town and in a pure residential areas. But in general, this is the distribution. Always the commercial buildings are being filled with less people than just by the book of the nominal capacity of the building. So this is one thing we have. In residential, we're putting more people than the nominal capacity, and in commercial less. So then we need to continue seeing how this look like. And basically, the reason that happened is that, so basically this very incredible plots, what it's telling me is that that effect in the distribution is like the income. I can tell you the GDP, which is this ratio, but another aspect is you have the rich people, the less rich people, so on and so forth. So what I'm showing here, in a given day, we have cluster, we have types of residential places, meaning the buildings in which, in the blue here, cluster 1, 20% of them, people do not leave the house. In the cluster 2, which is 50%, the majority, the buildings are 50% unoccupied in the day. So 50% of the members of that buildings are commuters and then come back. And in others, yeah, most everybody leaves the house. So people stay, half of the people leave, everybody leave. And similarly, we have commercial buildings that are not very full, and some that are pretty full, and we even have some that are more occupied in the night. So different types of occupancy in our buildings. And now that we have this, we need to test. That's new occupancy that I do with phone data. What's new? How can it inform or affect the energy models? Remember, the main goal of this work was energy model. Then here is, we have in this reference in the bottom, Carlos, our co-author, with Christoph, the advisor. They have a very careful model with Energy Plus in the Back Bay area. If they have it in Boston and we focus in Back Bay, basically here is the shapes of the building, how this is done. If you are interested in this part, there is a reference, but I mentioned Energy Plus is what tells me, I give you the buildings, you give me the output of the energy. What is it that they do in the MIT lab of architects? They have a plugin that you can have the GIS files together with the archetype, that is the typical information Energy Plus already used. And what this gives you is this beautiful 3D Rhino models that take into account shading and everything. So basically, this is an improved or enriched version of Energy Plus for architects. And what is special about Christoph Group is that they don't do it more in the architectural, that is building by building. They do it for thousands of buildings. So that is what that world came into about, and they work without phone data. They work with all the physics of the building and they nominal capacity, you know, by the textbook, according to DOE, this building, how many people can have. That is what they have. They use these models without any phone data. And basically, we are going to compare in all these buildings, what is the output of the energy consumption? You can see that that is the standard output without phone data versus what the information of phone data is bringing into the picture. That is what we're going to show you today, is without our work, with our work. Then, first and all, look, and this is the slide you would have to remember about the results, is right now, according to the estimate of DOE, because they use a nominal capacity, you see the black line. So at different time of the day, how many people we have in residential areas, and this is the black line. So in general, for this Boston area, looking the nominal capacity of the building between 50K and 100K, most of the time in all our residential buildings. Then we ask, what is the mobile phone data estimate? This game I described to you is the blue line. What is the census population of Boston? We only have one fixed, it doesn't change over time, is basically in the area we are describing in the Back Bay, in the track Back Bay, is this one. So the thing is, in a nutshell, that doing energy model by capacity of building is overestimating that 3 times the amount of people that you have in there. And then we have the population flux. Of course, DOE doesn't know so much about population flux. The mobile phone data is super good into that. So that is which this means is how many people is moving in the day and how many people is staying in this one track. Then, in few words, for residential and commercials, we can ask the data, what's the difference hourly on average that we have in residential buildings and in commercial buildings? And it's about 10 more people. According to the DOE, per building, you have 10 more people in everywhere. How this affects the current estimate? And that's the type of things we do. Just to give you a building by building case, because I know that we go all the time from the aggregate to the buildings. This is one apartment. What is the occupancy in the entire apartment building? Then we have that about 22 people live there, they move and they come back. In that example in our model, remember the little movie, for that particular apartment, using only phone data and building data, we match nicely the 15, it goes down, it goes up. This was a beautiful example. In this case, apartment 2, it was the typical example that our phone users were like this, and this was the capacity by DOE. Then, building by building, we have all the difference. This is the occupancy of DOE. This is the 5 cases from the distribution of the previous slide. Okay, so far so good. You already heard DOE is overestimating a number of people everywhere, but energy is not only about occupancy. It's about what you have in the building and what you use while you are in the building. It's the energy plus model. Then what we do is occupancy into energy plus, and you say energy plus, use my occupancy with phone data and tell me your output. We have 2 ways. One way is only use my occupancy. I call it high impact. It's just forget DOE, use my new estimate. And the other is, well, not necessarily just use the temporal aspect of the curve. Don't completely also take into account the capacity. So it's like a lower bound, upper bound of the impact of the scenario. Again, the question is how the uses in building, the new estimate of uses in buildings is going to be affected by using estimate of occupancy with only phones versus what is there, no phones at all. Here are the results for different places. Occupancy, as you already know, was one aspect, and then this is lighting. Watts per area in this apartment. In equipment, in apartment 2, watts per area, and then in apartment 3, we always do the peak. We're comparing the peak of how many hot water. So in a mall, everywhere in these places, we have output of energy plus is the solid line. New output with phone data, you have 2 scenarios. The one that you have only phone data, forget the DOE reference, is red. Sometimes it's very different. And the other is, okay, use the 2, basically, is the blue. So we have previous results, new result, incorporated, red results, only phone data. So these are the new type of results. And then these are the typical curve in winter aggregated. So in a given day, what is the total winter electric consumption with the 3 scenarios per hour, all the area that we study. And this is the distribution. So this is the total per hour, and you do the histogram in which every building in a year contributes to this histogram. And then again, what we have, a solid line is without this work, blue line is the lower bound incorporation, red line is the new. So we have new results, and then we have left-hand side is residential, right-hand side is commercial, and again, here is daily, total daily. So everything to add up energy use with DOE and with phone data. That is the whole story. And then this was a part, and this is the final piece of information or the slide is, okay, phone. I do know the new energy, but so what? Okay, I know the energy, but I want to do interventions. And then we say, okay, let's do one example, how these new estimates are going to inform my intervention. And the intervention of the left is I'm going to insulate the roof of all residential areas. I'm going to add 10%. If I do the cost of adding that, I want to know how much energy I'm going to save. The reference case, this is 4% you're going to save if you do that. This is the estimate based on only the existing models without phones. And the estimate tell us with our new result, hey, wait a minute, we're gonna save more than the current estimate. So basically, if you have different energy outputs, the interventions are gonna be, the estimate of the saving are gonna be affected too. And then finally, in the right-hand side, we have an interesting case. If you change all the plugins in the commercial buildings, are you going to save gas? Yes, but no, the story here is, here the label is opposite. It was a case that by changing the plugins, you save electricity, but you don't save gas, because the fact that you have the old plugins help you keep the building hotter. Then sometimes you are saving electricity, but then you don't save gas. Those are small cases, exercises in which if you have the current consumption, then you do something in the buildings and then you see the output. Then basically you need to know what are the current estimate of energy to see the power of the interventions. So to wrap up, we have demonstrated a method that uses available fund data. It can be done immediately. Same code, the program doesn't care if we do it in Sacramento, in Davis, in Berkeley. So everywhere we have fund data, we have POIs, we have buildings. So it's a portable methodology. What we found is the commercial buildings operate under capacity, and there is variations, a lot of variation in the estimates of residential buildings. The urban building energy models overestimate occupancy a lot, and this brings potential mispredictions. And this highlights the need to incorporate information and communication technologies data into energy models. And with that, I would like to open the moment for the Q&A.
Great. Thank you so much, Professor Gonzalez, for a great talk today. And we're going to go ahead and do our Q&A portion now. And so if you would like to go ahead and ask a question, if you can go ahead and raise your hand, there should be kind of an icon on the bottom of your Zoom screen. If not, if you can just hover over it, then it will pop up, and just raise your hand. And then Sandra on our team will go ahead and call you and unmute you. However,